Start my time.
Our next speaker is Faye Jackson, who will talk to us about the Bergman game.
Awesome. So this is work that I did with at Small with Steven Noor, who is over there, and I did it with many co-authors. So something you might figure out about me is I really enjoy sharing mathematics, and I really enjoy thinking about things with other people. And so I did this with many other people as part of the RU. I won't go through all the names, but they're all wonderful people. And there are two of them who are here. So Alicia and Irfan are both around, and Alicia is back there. And so let's go ahead and get started. Oh.
Just use the mouse. Click on the mouse.
Okay.
The real mouse.
Wait, that's what I did.
Click with the mouse and the remote.
No, neither.
But that's
No, the other one.
that's the wrong remote.
Wait, no, neither of them. Is there an ordering here? I think we're.
See, that was my job in the.
Oh, so I clicked on it with that mouse and then it didn't.
Let's now see if it works.
Neither of these work.
No,
Don't
that's
touch
not. No,
that one.
Okay,
that one too.
it's fine. I can click it with this. Okay, so let's just get started. So the Bergman game is this turn-based game that we created, which is based on two types of moves, and it's played on a double infinite tape with tokens. And so the first move is a combine move, which takes two tokens in adjacent indices and moves one to the right index, as so. And then the second move takes two tokens at the same index and splits them up in like so, and it moves this one token this way and one token this way. And so if any of you are familiar with the Fibonacci numbers, you might notice. And so let's just go through a quick example of how you might play this game. So we're going to start with 9 tokens in the 0th index. And what we can do is our first move, we can split 2 of those tokens off. And 2 of those tokens move here and here. And then we're left with 7 tokens in the center. We can then split again. And then just going through, we could combine these 2 tokens here and make a token right here. And then going through again, we can combine, split, combine, combine, combine,
Each
and
stage
split.
is there only one legal move so far?
No.
Oh.
So observe, for example, at 411, you could also split this 4, or you can combine these 2 right into this index. So at any stage, there are multiple legal moves. At most stages, I mean. There's no legal moves here because there's no legal moves whatsoever. But the general idea of the game is that at the end, you see which player was the last to move, and they're the one to win. So in this case, I think that player 2 wins, although you might have to check my two-adic analysis. And so, so we all love the golden ratio, and the characteristic polynomial x squared minus x minus 1 for the golden ratio works extremely well with these moves. And the reason is that, of course, x squared is equal to 1 plus x, and you should think of the exponents as representing the indices in this game. And then 2x squared is equal to 1 plus x cubed as well, just via some simple algebra. And of course, the golden ratio is a root of this polynomial, as we all know. And there's a sort of corollary of the game, which was invented much before the game was invented by Bergman. And there's this fact that any integer can be uniquely represented as a sum of non-consecutive powers of the golden ratio. And so the original way that this was proved and thought of was you used the greedy algorithm to produce the decomposition. And so an alternative way of thinking about this game is just an alternative algorithm that is not greedy. And you might ask, why would you not want a greedy algorithm? Those are generally very fast. They're also very imprecise. So if you're working on a computer, you have floating point numbers, and you can't directly measure their difference very easily. And you might get errors. In fact, if you try and decompose numbers using the greedy algorithm on a computer, you'll run into wrong answers. And so just to go back, each index represents a power of v, and the moves, because the characteristic polynomial is so nice, do not change the value if you sum over the powers of v. So this would be like 9 times v to the 0. This would be v to the -2 plus 7 plus v to the 1. And then as you go through, you're essentially decomposing this number 9 into its base b decomposition, which is when we're going to be calling these things. And that's b to the -4 plus b to the -2 plus b to the 1 plus b to the 4. So what can we say about the game? Well, first, let's get into some history. So I believe you all know about the Fibonacci numbers, but within this talk, we're going to start them a little bit differently for convenience. So we're going to start with 1 and 2 as our initial conditions. And with these initial conditions, there's a theorem, Seckendorf from 1972, that's quite famous. Every positive integer can be written uniquely as a sum of non-adjacent Fibonacci numbers. And so, of course, the example of 2022 to represent the year, we have this decomposition into Fibonacci numbers, which is quite nice. And the inspiration for the game that we created, which you might have seen in the Far Difference game yesterday, is the Seckendorf game, which uses very, very similar rules to the Bergman game. However, has extra boundary moves that are kind of strange and don't follow the same rules. And so our kind of inspiration was that these boundary moves were nasty. And what happens if we get rid of them and play the game the same way everywhere? And this produced the Bergman game. And we kind of discovered by accident that it produced base B very early on into our studies because it kind of fell out naturally. And this produces Seckendorf decomposition. So you can kind of think about decomposing a number into Fibonacci numbers as being kind of similar to decomposing it into the powers of phi for fairly clear reasons. And so, but they are different games and they have much different behavior. So say you play with 20 chips. So you're decomposing the integer to 20 and you're playing the Seckendorf game on the left. And each black square represents a cell with an index or a token on it, or more than one token. And each row represents a game state. And this is the Seckendorf game, and this is the Bergman game. And you'll notice that I've zoomed out of the Bergman game very, very much. You'll also notice some interesting patterns of sort of collapsing of information. This is because we use a very particular strategy in the Bergman game to create this picture. And so generally, the Bergman game is much, much more complicated and more difficult to analyze. We'll see this in a few ways. So there are some techniques that we can use to analyze it. And they're techniques that should be familiar to anyone who enjoys algorithms. And so kind of the inspiration for these techniques is monovariance and invariance of a game. And so the principal invariant that I've already been talking about is the value of a game state. That's what I like to call it. And this is the integer, or generally it can be any combination of power of phi if you play from different initial conditions that you're representing as you're playing the game. And so this doesn't change. You can see an example here. And so it's an invariant. And for convenience, I'm going to use, for any game state S, I'm going to note by S of j the number of tokens that I placed at index j. So that's the formula for the value. And value is useful, but it's not very useful if you want to prove termination, which with a very long game, you should try and prove it terminates before you do anything else. So a more useful invariant for proving termination is actually the number of chips. And you might notice that the number of chips is not very natural to consider a priori if you're doing things from the point of view of decompositions. I mean, you could consider this a number of summands, but it's a little bit less natural. And so this always goes down as you take any combined move. But if you take a splitting move, it stays the same. So essentially, this bounds the number of combines by the number of chips you start with. And then it suffices to prove the game terminates to bound the number of successive splits. That is much more difficult than one might imagine. And so let's see how we're going to do that. So this one is a very nasty which you might come up with if you are a despot. Which I think and so essentially you weight the sum of the indices instead of by powers of phi, you choose your weighting factor to be actually just the index position itself. When you see a split decreases by 1, which is simple algebra, and you can bound the number of successive splits so long as you can bound this index sum itself, which is a little bit different. And combined index j actually increases this by negative j plus 3. So now you can wonder how are you going to bound the number of top and bottom. And so it suffices to get a left and a right bound on the total game state because the number of chips is always bounded above by however many you started with, right? And so the first establishment right now, this is very easy. All powers of p are positive because p is positive. And so what you can do is just go log base b to the value of s to the right. If you go any farther than that, then you're way too big to decompose the value. And so that's easy. This can be extrapolated away into a left bound. And so what you can do is you can bound the maximum gap size, where a gap is a string of zeros between some during any part of the game. And the technique for doing so is essentially to realize that a split can only create a gap of size 2, essentially because it sends a 2 and it sends 2 1s to the left and the right. So it can't create any gaps. And the number of combines is very bounded, and it can only create at most 2 zeros for any combine. And so because of that, you can kind of bound the maximum gap size during the entire game and perform a worst case analysis. Place a 1 at the rightmost bound, go as far as you can before having another 1, go as far as you can, go as far as you can, go as far as you can. It's beautiful in a way. However, it is very, very not optimal. So this gives a maximum and minimum for the index sum. And with this, you can prove the Bergman game terminates, but it's really bad. So your at most number of chips combines. Chips and tokens I use interchangeably. We use a lot of notation. And so it suffices to bound the number of successive splits. And this is bounded because the index sum is bounded below, and each split decreases the index sum by 1. So you might wonder how fast this termination time is, especially if you want to think about this as an algorithm for producing these decompositions. This proves an exponential time termination, which is really awful. It's not what you want in any case. And so you might wonder why we did this. And because eventually the theorem is going to be a polynomial time termination. The trick is actually that you need this to start. And this is actually my favorite trick in the entire talk. And so I always call this building better hammers. And so essentially, you first prove slow termination. And this is kind of like a baby hammer that you give to a child. And then what you do is you say, okay, I know that I'm going to terminate in a base B decomposition. And base B decompositions are extremely well studied. So what do? You take information about the final state and you think about the game. And you think closely about the game and what you can do to get information about the left bound throughout the entire game. Any information about the left bound is going to give you a fast termination time. And so now you can get fast termination, which depends on the length of the initial state. And I won't talk too much in detail, but you can do even better than this. And so you can take fast termination, which depends on the length of the initial state, go to the ending state, look at the base B decomposition, use information about the base B decomposition, and travel back on it, in a sense, and show that it actually only depends on the number of chips, which is sort of a miracle that I didn't expect. So actually, my colleague, Ethan Petzoff, and I debated this for many weeks, essentially, whether this was true. So we eventually called this airplane hanger principle, which is that if you have a ton of chips distributed very far apart, then they shouldn't be able to interact too badly, because all of our moves are local in some sense. And so because of that, they shouldn't be able to interact. But we spent a long time trying to come up with counterexamples, and we actually came up with some interesting game states that we like to call cogs. I can tell them to you about this afterwards. But essentially, you can go to the final state and take back information. And that's kind of the whole moral of the story with this game. And so I'm going to kind of go through the second bullet point in a little bit more detail. It's actually very elementary, which is kind of amazing because it was a very difficult idea to come up with from us, because you don't expect to prove the really strong result by using the really, really weak result generally. And so the trick is that there's a left bound of not negative log phi n on the leftmost summand in the final state, which is of course the base p decomposition, that begins with n chips at the 0th index. And there's a tight bound of negative 2n minus log n on the leftmost used edge across the entire game. So if you keep track over the entire game of the farthest left you've gone. And so the trick here is you apply algebraic number theory for the first piece. And this was a result that was published in Fibonacci Quarterly, in fact, in more generality, which I'll talk about in a moment, in order to bound these base P decompositions. And I think that was done by Bergman and Solomon. And kind of the trick here is that you indeed terminate. So if you didn't know that you terminated at all, you wouldn't know you terminated in a base P decomposition. So you need to know that first. And that's kind of the trick. And then once you do that, everything's easy. So split sends the summand to the left. So it can't affect that leftmost summand that's used. And because of that, it can't move the leftmost summand inward. But a combine can move the leftmost summand at most 2n. And because there are at most n combines, because of the number of chips always going down when you take a combine, you actually get this negative 2n directly from that. It's extremely simple, but also extremely beautiful. So before we had this proof, which was a later development, we had an earlier proof, which was very, very nasty. So we had a very analytic argument, which established this directly. And it's kind of relies on this idea of approximating zeros in base P. And this was very difficult. And worse, it only works in base P. So I'll talk about some generalizations in a moment. But that method only worked in base P. And if you go to the other bases, it's incredibly difficult. And so going on, and yes, I call it embarrassingly long. This is much better. So I'll just summarize the results for the Bergman game, which is that the longest Bergman game with n summands, regardless of where they're placed, and place them wherever you want, be creative, that terminates in theta of n squared loops. And furthermore, if you choose a particular strategy, which if you like to talk about the strategy later, I can talk about, you can achieve an O(n) game. So essentially this gives, if you want to think about it algorithmically, I kind of switch between the perspectives, this gives a exact vector-based algorithm for computing these decompositions in linear time in the integer you're decomposing, which is kind of neat that you can think about it this way. And it's much better than the greedy algorithm if you want to be precise. And then, so the generalized Bergman game requires a small bit of background about positive linear recurrence sequences. And so what you do is you start with this recurrence sequence with this particular characteristic polynomial, and you require that the first and the last coefficient are non-negative, positive, and also that you have at least 2 as your order. And then you say it's non-increasing if they follow this sequence. And for convenience, if j is greater than k, we often let cj is equal to 0. Okay, so an example is these initial conditions in this recurrence relation. I can't remember when we came up with that. So the generalized Bergman game is extremely similar to what we started with, except we start with much more complicated moves that kind of ensure that you end in the base beta decomposition, where beta is a dominating root of that recurrence. And so you might have heard about Piso and Salem numbers. So actually that dominating root will be a Piso number. And so it's kind of nice, the connection there. And so the Bergman game is based on those. And so you create other moves that are quite similar. And we were able to prove using exactly the same techniques that you terminate in theta of n squared moves. Now, some notes on this. I think this is, in fact, a novel proof that there do exist base beta decompositions for betas of this type. So the proof that base beta decompositions exist in general is using ergodic theory. And so this is quite different and much more elementary, and kind of interesting that in this special case you can get that. To go a little bit further, the way this is proved is actually where we need the algebraic number theory from earlier. In the base B case, you can do something kind of special and kind of rig the game a little bit. It's not quite as beautiful in some way, but you can get something much quicker. So, and much more elegantly. Okay, so some quick further questions before I finish up. So in the second dwarf game, it's known that the second player always has a winning strategy, so long as you're playing with at least 6 chips. We have no idea what's true of the Bergman game. And I'd be very, very, very interested if someone can answer that question. So the proof for the second dwarf game relies on a strategy scaling argument, and it's non-constructive. If you try and run the same proof for the Bergman game, then the game tree explodes, and you can't do a strategy scaling argument, which is quite unfortunate. And I mean, maybe we just haven't computed far enough and something collapses somewhere, but I doubt it. And then, so if there's not a winning strategy for one player, as long as you have enough chips, then you could ask how hard it is to determine who wins, given how many chips you have. And then we also want to see how far these results can be pushed beyond these non-existing PRS games. And even to them, there are some results of the Bergman game, particularly the fast termination time that we don't have for the generalized Bergman game. And a quick note before I finish, the second bullet point, we have something approximating a result about that. Namely, we know that if you play a game on a graph, so for this whole time we've been playing on a doubly infinite tape, if you use very similar rules to play on a graph, you can actually embed this game, or you can embed the game set into this game, which means this game is very, very hard to determine who wins. In fact, it's something called p-space complete, which is harder than NP hard, and very, very difficult. So this is strong evidence that it's actually very hard to determine who wins in the Bergman game. And in fact, strong evidence that there's no constructed proof in the second dwarf game in some sense. And so I think that's the end. I want to acknowledge that Stephen J. Miller is an excellent, excellent mentor and very nice to me. And we were funded by the NSF. And special thanks to all of our co-authors on this paper. I love all of them. Here's a picture of some of them where we went on a hike, and I think that's me. Is Alicia in this picture? I don't know if he went on this hike. Nope. Okay.
Then what I'm adding for now.
Hmm?
If not, I'm adding for now.
Okay, great, and so, yeah, this is very fun research. Thank you very much.
Question first. Can you open the slide with these steps, moves?
The first slide.
So there are 2 moves. So combine and split. How do you choose at each step which move you apply, combine or split?
Yeah, so if you're playing it as a game, then you choose based on strategy, right? So it's just you choose based on what you want to do, right? Or what each player would like
so
to
it's
do.
random. You want to choose
Yeah.
combine or split, whatever.
Yeah. As far as if you're viewing it as an algorithm, then there is a best strategy for terminating quickly. In this strategy, I may get the directions wrong, but I think you always want to combine as far to the right as you are able to combine. And then if you can't combine, you split farthest to the left. I think this is optimal for terminating quickly. Essentially, this should be optimal because you make your biggest components as quickly as possible. And there's a proof of that in the paper, but it's actually quite messy. You have to do a little bit more than you'd expect to get that terminates quickly.
So to terminate, you need to apply both moves, combine and then split.
Yes, so applying one of them is not sufficient.
Combine, the process will never terminate. Right?
Yeah, in fact, you can't. If you only decided to apply one move, then you would terminate, but you wouldn't terminate in the base PD composition, which is quite important for all of our analysis.
Any other questions? Yes.
Yes, you can start the game and chips lying anywhere on the street. And is it true that the longest game is achieved when all the chips lie on the same square? Or
Asymptotically, this is true because we proved that you terminate in theta then squared time. And we in fact proved that to prove the lower bound, we proved that the game with n chips in the center terminates in n squared time. I have no idea if that is true in terms of the constants in front of those asymptotics and things of that sort. But yeah, it's a quite difficult question. The methods give you the constants, but they're very nasty and they don't agree between the lower and upper bound. They're very close.